Hello everyone, thanks for watching this video. I'm Jiangong Chen from Penn State. Today I'm going to present our paper PRISM-XR, Empowering Privacy-Aware XR Collaboration with Multimodal Large Language Models, which is co-authored with Mr. Mingyu and Dr. Bin Li. Multimodal large language models are becoming increasingly popular as it can accept multimodal inputs and generate various types of contents like plain text, coding scripts, images, or videos. But certainly it can also revolutionize the XR experience since it can enable users to build and modify virtual objects or animations with natural language. For example, as shown in these images, one user can create a virtual whiteboard onto the real-world wall, and the other user can update the virtual markers properties. And after that, they can draw on this whiteboard, and one user may ask questions to let MLLMs to solve their issues. So the goal in this paper is to provide seamless multi-user collaboration in a shared physical spaces, so the users can interact with both virtual and physical objects. To achieve that goal, we need to address the following challenges. First, usually we need to use cloud-based models as they have the highest capability. However, as we need to include visual data from the physical world and include them into the prompt to the models, it may raise privacy risks. And secondly, the physical worlds usually have tons of irrelevant objects that may distract MMLMs from the actual tasks. Thirdly, we want to align the virtual objects from all users to the physical worlds. However, existing commercial solutions usually time-consuming and have privacy-invasive environment scanning. And lastly, we want to synchronize the virtual objects to all users. However, the traditional network synchronization mechanisms usually struggle with the dynamic nature of MLLMs. We can further condense the both challenges into these three research questions. First, how could we prolong the visual inputs so that we can protect the user's privacy while maintaining sufficient context for MLLMs? And secondly, is there a low-cost, accurate, and also privacy-aware approach to align the users in an efficient way? And lastly, could we synchronize the objects and animations generated by MLLMs in an efficient way? To solve the questions, we propose PRISM-XR with a three-tier design. First, on client side, we capture audios and images from the user's field view, as well as rendering the objects animations in XR environment. Then, in an edge server, we perform reasonably complex tasks like speech-to-text and object detection via some machine learning models. And also, we deploy our customizable collocation and synchronization mechanisms on the edge server. Note that we treat the client and edge server as a privacy-preserving zone as they are fully controllable. And in contrast, we have the cloud server as privacy-risky zone since we will communicate with business-managed MLLMs. One of the main designs in our paper is the privacy-aware frame processing. So first, the user captures the screenshots via their headset, and then we conduct edge-assisted object detection on the edge server. The detection results will be converted to a textual summary and is involved in the prompt to the MLLM, and we let MLLM decide whether visual information is needed. If so, it will decide the cropped coordinates, and then we leverage the cropped coordinates in the edge server to crop the original frame and send this cropped frame for user for confirmation. And the user will see a pop-up window like this, and it can decide whether it includes sensitive or not. If not, it will be sent to the MLLM for further processing. Otherwise, it can be discarded and for another try. To facilitate the user collocation, we propose a registration approach to combine the marker-based localization and very initial odometry. So each user will be asked to step in front of a April tag marker and initiate a voice command registration. After that, the system will automatically calculate the pose and store them in a shared space. And by simple transformation, we will know all the virtual objects position in all users' coordinate system. So if the registration is successful, we will see a blue cube rendered on this marker. Otherwise, the user can try multiple times until it observes that. So after the registration, the user are free to move anywhere and without the constraint on this marker, since it will rely on the internal very initial odometry. Tailored for the dynamic MLLM environments, the other design we propose is a customer edge protocol to synchronize the content with two categories. So the first one is for the MLLM responses. So we will, since it can have owner specific dependencies, we will first stream the response to the requester and then convert it to a shared physical spaces. After that, it will then be broadcast to all the users. On the other hand, for those user interactions with the virtual objects, we will ensure the streamed coordinate space is in the shared space, and those responses can be streamed in with optimized payloads to ensure a fast and seamless interaction. Given those system designs, we have implemented our system into commercial XR devices like Meta Quest 3 and Microsoft HoloLens 2. We have developed the system with Unity and corresponding SDKs, and we deploy at server via Python scripts and running on the local workstation. We have deployed the following AI models either on the edge server or on the cloud. To evaluate our system, we first conduct a system-level numerical study. Like here, we have listed the accuracy of MLM responses in both the initial stage and the refined stage. We can easily observe from this table that the cloud models like O1, O3 Mini, and GPT-4o can achieve significantly better performance compared to those edge models. This inspires us to use the cloud models, even though they can raise privacy concerns. On the other hand, we can observe that GPT-4o achieves the best balanced performance, so we deploy it for our user study. We have also measured other metrics like the collocation accuracy and the end-to-end latencies, but here we omitted them due to time constraints. Please refer to our paper for more details. Besides the numerical study, we also conducted a user study with 28 participants in 14 groups. We asked the participants to conduct a series of tasks in a controlled lab environment. In this lab environment, we have manually created lots of sensitive objects, including the medical records, or personal staffs. So to validate the system usability, we have also collected other various types of usability metrics. As for the privacy metrics, we have let the participants classify those 12 categories of objects into 3 different privacy levels, and we then manually count the ratio of frames, including those objects in different privacy levels, before and after the privacy-aware frame processing approach. Given the results, we can observe that the ratio of the frames including the highly sensitive objects is reduced from 53% into 7%, indicating that our approach can efficiently exclude those sensitive objects from uploading to the cloud server. We also have other usability metrics in the user study. However, we omitted here due to the time constraints. Please refer to our paper for more details. In conclusion, our paper designed PRISM-XR, proposing with the privacy-aware frame processing and a customized synchronization approach. We have implemented it into commercial XR devices and have conducted both numerical study and user study to assess the privacy, usability, and also the feedback for future directions. We have also open sourced our system into the GitHub repo. Please scan this QR code for more details. Thanks a lot for watching this video. Please feel free to let us know if you have any questions. And also, you are encouraged to attend our live presentation during IEEE VR conference. Thanks.